What you are seeing is a condensed demonstration of an important step in the evolution of the TAAIB vCPPS platform. This is not just a software feature. It is part of Tiemac's broader approach to helping manufacturers adopt AI in a structured, practical, and de-risked way. Before AI can be useful on the plant floor, the manufacturing environment must first be organized, contextualized, and made understandable to the intelligence layer. That begins with simulation scaffolding and the AAS structure. Here, the TAAIB vCPPS platform demonstrates the ability to upload and associate unstructured documentation with the correct AAS models and submodels. This is much more than document storage. It means an OEM manual can be tied to the exact machine it describes. A maintenance SOP can be linked to the process area it governs. A bill of materials can be associated with the relevant SKU. Operator notes, work instructions, troubleshooting guides, and quality documents can all be connected to the correct digital asset. This turns scattered manufacturing knowledge into structured, retrievable operational context. That is essential, because AI should not reason from isolated files. It should reason from knowledge that is grounded in the actual structure of the plant. This document type feature capability is especially important for the intelligence layer and its Retrieval Augmented Generation System, RAG. In many AI deployments, RAG is treated like document search. TAAIB vCPPS platform takes a more industrially grounded approach. Documents are not placed in a generic knowledge base. They are connected to the AAS hierarchy, alongside machine context, process context, production flows, telemetry, behavior profiles, and AI model outputs. So, when the system analyzes a machine issue, it can reason from sensor readings, maintenance history, operating constraints, and relevant documentation together. That is the difference between an AI tool that talks about manufacturing and an AI system that begins to understand manufacturing.
The TAAIB vCPPS platform's intelligence layer draws from four major sources. First, streaming and transactional data, including telemetry from InfluxDB and operational records from MongoDB. Second, outputs from descriptive AI and machine learning models for anomaly detection, predictive maintenance, and forecasting. In addition, it uses outputs from Tiemac's patent-pending Greedy Random Adaptive Search Procedure, GRASP, plus Reinforcement Learning, RL, AI approach for conditioning plant operations towards more good operating days than bad operating days. Third, the structure of the plant. The AAS-based digital twin, including machines, sensors, actuators, WIPs, SKUs, BPs, AMBPs, and operating constraints. Fourth, unstructured documents such as manuals, SOPs, BOMs, operator logs, and work instructions. This is why the document upload capability matters. It connects human operational knowledge to the AI system in a way that is structured, traceable, and useful. The development of the TAAIB vCPPS platform's intelligence layer was advanced through Tiemac's Spring 2026 engagement with Georgia Tech Senior Capstone students. With Tiemac's TAAIB vCPPS platform's designed architecture and framework, mentoring, and technical guidance, the Georgia Tech student team worked against a defined intelligence layer development brief using a grain and cereals manufacturing use case as the reference scenario, but with applicability for any discrete, continuous, including electricity generation, and/or hybrid manufacturing plant operations. The project was not simply theoretical. The requirement was to support working deployable capability aligned with the TAAIB vCPPS platform architecture. That matters because it demonstrates that the platform is structured enough for an external technical team to understand, extend, and build against. It also shows how Tiemac is helping connect industry academia, and the next generation of engineers around physical AI for manufacturing. As part of the TAAIB vCPPS platform's intelligence layer, there is a focus on descriptive AI, machine learning, GRASP with RL. This includes Apache Spark, distributed computing data pipelines, exploratory analysis, anomaly detection, predictive maintenance, and deep learning with temporal forecasting. The goal is to help the platform recognize operational patterns. Is a machine drifting from normal performance? Is downtime risk increasing? Is throughput changing? Is the plant moving toward a good production day or a bad one? These questions require data, models, and measurable outputs. This focus on descriptive AI, machine learning, GRASP with RL, gives the TAAIB vCPPS platform's intelligence layer quantitative grounding. The TAAIB vCPPS platform uses the built simulation scaffolding, digital twin, and the smart manufacturing vCPPS to provide the structural and physics context. The TAAIB vCPPS platform does not want AI outputs that sit outside the plant model. It wants those outputs tied back to machines, process areas, sensors, actuators, SKUs, WIPs, BPs, AMBPs, and operating constraints. An SKU, product, forecast, is more useful when it belongs to a process area. An anomaly is more useful when it is tied to a specific machine and sensor. A recommendation is more useful when it can be checked against the plant hierarchy. That is what the AAS-based digital twin provides, and this forms the organizing backbone for manufacturing intelligence.
Within the TAAIB vCPPS platform intelligence layer is governed Agentic Gen AI, tailored specifically to a manufacturing environment. The Agentic Gen AI is not designed as a generic chatbot sitting on top of the platform. It is part of the controlled intelligence layer that helps users ask meaningful questions about the vCPPS plant, retrieve grounded answers, and move from general understanding to more specific operational insight. The first interaction mode is the quick mode. This is useful when a user wants broad, generalist information about the vCPPS plant. For example, the user may want to understand the overall plant structure, the purpose of a process area, how the simulated plant is organized, what the main production flow looks like, or how different parts of the digital plant relate to each other. In this mode, the Agentic Gen AI layer acts as an accessible guide to the vCPPS environment. It helps users understand the plant without requiring them to manually inspect every process area, machine, sensor, actuator, or AAS object. The second interaction mode is more specific and more operational. This is the human-in-the-loop mode. Here, the user can select a particular area of the plant, choose a specific machine or asset, and then select from prepared questions designed to produce more targeted intelligence. This matters because manufacturing users often do not want open-ended AI answers. They want relevant answers tied to the part of the plant they are actually examining. So instead of asking the AI something vague, the user can ground the question in a defined process area, a defined machine, a defined AAS structure, and a defined operational context. The response can then be shaped by the plant model, the machine context, the available documentation, the telemetry, and the outputs from the descriptive AI models. What makes the TAAIB vCPPS Platform Intelligence Agentic Gen AI layer is its unique 7-module architecture. Buckets, Director, Booster, Enforcement, Story Game, Helpers, and Helpers_utils. Together, these modules help structure the user's request, assemble the right context, apply guardrails, enforce constraints, generate useful responses, and keep the interaction aligned with the operational purpose of the platform. The goal is not to let the language model freely speculate. The goal is to make the model useful inside a manufacturing decision environment. That is why the TAAIB vCPPS platform emphasizes context assembly, traceability, constraint validation, human review, and explainable responses. When the Gen AI layer provides an answer, recommendation, or draft logic, that output should be connected back to the plant structure, the relevant data, and the governing constraints. Another important point worth mentioning is deployment. TAAIB vCPPS platform uses an open-source Mistral-based LLM approach for secured, localized AI deployment. This supports Tiemac's private cloud strategy and helps avoid unnecessary dependence on black box external AI services. It also gives manufacturers a more controlled path for protecting sensitive operational data, plant knowledge, and proprietary process information. This is especially important for industrial AI. Manufacturing companies need intelligence, but they also need security, auditability, control, and trust. TAAIB vCPPS platform approach is not simply about adding Gen AI to the platform. It is about adding governed, localized, context-aware agentic Gen AI that can support real manufacturing users. Quick mode helps users understand the plant at a broader level. Human-in-the-loop mode helps them ask specific, grounded questions about selected areas and machines. The 7-module Agentic architecture governs the interaction. The Mistral-based local deployment supports security and control. Together, this gives TAAIB vCPPS platform a practical Gen AI capability designed for physical AI, not as uncontrolled automation, but as explainable intelligence that works within the structure, behavior, and constraints of the virtual cyber-physical production system.
Another important capability shown within the TAAIB vCPPS platform intelligence layer is root cause analysis. Here, the platform moves beyond simply reporting that something has happened. It helps the user begin asking why it happened. Through the human-in-the-loop interface, the user can narrow the context by selecting a specific process area, machine, or operational condition. From there, the governed agentic Gen AI can use prepared questions to guide the analysis in a controlled way. For example, if the system detects a throughput drop, abnormal vibration, quality drift, or process delay, the user is not left with a generic alert. The TAAIB vCPPS platform intelligence layer can examine the relevant telemetry, AAS structure, machine context, BP, and AMBP behavior patterns, historical records, and supporting documentation such as maintenance manuals or SOPs. This creates a more grounded explanation of possible causes. The value is that the TAAIB vCPPS platform does not treat root cause analysis as guesswork. It uses the digital structure of the plant, the live or simulated behavior of the vCPPS, and the retrieved operational knowledge to help users move from symptom to likely cause. And because this is governed AI, the response remains explainable, traceable, and subject to human review.
The second related capability is the Optimization Studio. Once the platform helps identify what may be causing a problem, the next question becomes, what can be improved, adjusted, or tested? This is where Optimization Studio becomes important. It allows the TAAIB vCPPS platform intelligence layer to support scenario-based decision-making across the vCPPS plant. The user can explore questions around throughput, congestion, production flow, resource use, quality, downtime, machine behavior, or process bottlenecks. Rather than applying changes directly to the physical plant, the platform allows those ideas to be tested first inside the virtual cyber-physical production system. For example, if a process area is becoming congested, the system can help evaluate rerouting options. If throughput is dropping,
It can help examine machine performance, WIP movement, production timing, or control logic. If a machine is underperforming, it can help compare potential adjustments before escalating to real-world action. This is central to the TAAIB vCPPS platform value proposition. Optimization is not treated as a black box AI recommendation. It is grounded in simulation, AAS structure, descriptive AI outputs, governed Gen AI, and human judgment. The result is a safer way to improve manufacturing performance. Diagnose first, test intelligently, validate through the vCPPS, and only then decide what should move closer to real operations.
In this section of the TAAIB vCPPS platform walkthrough, the role of the smart manufacturing layer becomes clear. Simulation scaffolding gives the plant its digital structure. The intelligence layer gives the platform reasoning capability. But smart manufacturing brings the scaffolding to life. This is where the vCPPS operates. Sensors generate readings. Actuators respond. No-code PLC logic drives behavior. WIP moves through process areas. Finished goods accumulate. BP and AMBP patterns shape machine behavior. This matters because AI needs relevant data to reason about, and AI also needs a safe environment where cause and effect can be explored before touching real equipment. The TAAIB vCPPS platform smart manufacturing layer generates the data and is the living bridge between digital structure and deployable intelligence. The TAAIB vCPPS platform's deployment strategy follows a creep, walk, run model. In the creep phase, manufacturers can structure the plant, define assets, upload documents, and organize knowledge without disrupting operations. In the walk phase, the vCPPS brings that model to life through simulated behavior, virtual sensors and actuators, no-code PLC logic, telemetry, BPA MBP, and dashboards. In the run phase, the intelligence layer supports deeper AI-assisted decision-making through descriptive models, GRASP plus RL, RAG, optimization, and governed Agentic Gen AI. This staged approach reduces risk. It gives OT, IT, management, and operators a shared environment to evaluate AI before making high-cost or high-risk commitments.